Riemann sums and the definite integral. As an example, we want to find the area under the following curve. We want to find it between t equals 0 and t equals 20. The first thing we might try is to put a solid rectangle that starts out at a height of 60 and goes to time 20. Now, of course, this green rectangle overestimates how much area is under the curve. So maybe we might get a better estimation if we looked at the square at height 60 going till 10 days, and then the height at 10 days going to 20 days. So there we go. We've subdivided the interval in half. And in fact, we've lost a good amount of that extra area that was over approximating the area beneath the curve. Well, what if we did that again? What if we subdivided at 0, 5, 10, 15, and 20 days to come up with 4 regions instead of 2? Again, we'll use the height of the curve as the height of our box. You can see we've cut out another chunk of area that we were overestimating by. We can subdivide a little bit more, really until we're down to as many subdivisions as we want. And as the number of subdivisions goes to infinity, we have our 6th diagram there, which looks like the actual area. So mathematically, finding the area under the curve is exactly like finding the area of a bunch of rectangles and adding them up. So how do we do that mathematically? In general, we have a function f, and we consider an interval ab of possible values of the independent variable x. We subdivide that interval ab into some number of segments of equal length. We use n as the number of segments or subdivisions. Next, we label the endpoints of these subdivisions, x0 for a, x1 for the end of the first subdivision, x2 for the end of the second subdivision, and so on until we get to the end of the nth subdivision, xn. So xn in this case is going to be b. So a is equal to x0, is less than x1, is less than x2, etc., is less than xn, which is equal to b. The first subdivision is on the interval x0 to x1. The second subdivision is x1 to x2, and so on until we get to our last subdivision, xn minus 1 to xn. We're dividing the interval ab into n subdivisions of equal length. By doing that, since the entire interval is of length b minus a, and we have n subdivisions, each segment is going to have length b minus a over n. Rather than writing b minus a over n repeatedly, let's call that delta x. So what we want to do is for every subdivision, we want to compute f of x sub k minus 1. So that's the value of our function f at the left endpoint for each subdivision. So this will be the height value for our box. We then want to multiply that height value by the length of each interval, which we said was going to be delta x. We then add the length and width products together to get f of x0 times delta x plus f of x1 times delta x, so on, plus f of xn minus 1 times delta x. What we've made ourselves is what we call a left Riemann sum. For n equals 4, in this example, this is what the computation looks like. our left Riemann sum is going to be f of x0 delta x plus f of x1 delta x, etc. Because we have interval length of 20 and 4 subdivisions, each subdivision is going to be 20 divided by 4, or length 5. And so our left Riemann sum is f of x0 times 5 plus f of 5 times 5 plus f of 10 times 5 plus f of 15 times 5. So that's 60 times 5 plus 42 times 5 plus 28 times 5 plus 18 times 5. These are all sort of close enough based on our diagram. So this has area 740. Again, this is an overestimate, but all we're looking for is an estimate. Now, we use these sums so often in mathematics that we've got shorthand for them. In this case, f of x0 delta x plus f of x1 delta x, so on to f of x n minus 1 delta x. We say that that is the sum where k starts at 0 and goes to n minus 1 of f of xk times delta x. We can think of this as adding a bunch of things that look like f of xk times delta x. And our k is a counter that goes from 0 to n minus 1. The symbol that we see here is a Greek letter sigma, and it stands for summation. The letter k that we had was called the index of summation, and we can think of that as counting off the segments. We read off the notation as the sum from k equals 0 to n minus 1 of the quantities f of xk delta x. If you've ever used a loop, this is what we're doing. We think of this as a set of mathematical instructions. We start with k equals 0 and calculate f of x0 delta x. We then set k equals 1 and calculate f of x1 delta x. And so on till we get to k equals n minus 1, we calculate f of x n minus 1 delta x. Once we have all those quantities calculated, we add them up. So what is a Riemann sum? If f is a continuous function, the left Riemann sum with n equal subdivisions for f over the interval ab is defined to be the sum where k equals 0 to n minus 1 of f of xk delta x, which is equal to f of x0 delta x plus f of x1 delta x, all the way up to the sum f of xn minus 1 delta x, or f of x0 plus f of x1 all the way to f x sub n minus 1 times delta x, where x0 is less than x1 less than xn, are the endpoints of the subdivisions, and delta x is equal to b minus a over n. Now, if f is the rate of change of a quantity, capital F, the antiderivative of f, then is the Riemann sum of f. The Riemann sum of f approximates the total change of capital F from x equals a to x equals b. The approximation improves as the number of subdivisions increases toward infinity. If f of t is the rate of change of the number of bats in a belfry, for example, and the closed interval ab is closed interval 2, 3, then the Riemann sum approximates the total change in the number of bats in the belfry from the time t equals 2 to the time t equals 3. Graphically, we can represent a left Riemann sum of a non-negative function as an approximation of the area under the curve. The left Riemann sum always takes the box heights based on the left endpoint of each subinterval. As an example, let's compute the left Riemann sum for f of x equals x squared plus 1 over the interval -1, 1 using n equals 5 subdivisions. First, we need to find delta x. Since a, b is -1, 1, b equals 1, and a equals -1. Because we have 5 subdivisions, our n is equal to 5. So we have 2 over 5, or 0.4 as our delta x. So the subdivisions are going to be -1, which is less than -0.6, which is less than -0.2, which is less than than positive 0.2, which is less than 0.6, which is less than 1. So we increase in increments of 0.4. The Riemann sum then is f of x0 plus f of x1 plus f of x2 plus f of x3 plus f of x4 times delta x. So our 5 left endpoints each times delta x. We throw in our numbers. x0 is -1, x1 is -0.6, x2 is -0.2, x3 is 0.2, and x4 is 0.6. Delta x is 0.4. Adding them up, we get 2.72 as our area. Looking at the picture, it's difficult to say if this is an underestimate or overestimate because parts of this are overestimating the area. For example, from -1 to positive 0.2, and parts of it are underestimating. For example, 0.2 to 1. So if f is a continuous function, the definite integral of f from a to b is defined to be the limit of the Riemann sums as the number of subdivisions approaches infinity. So the integral from a to b of f of x dx, the definite integral from a to b of f, is equal to the limit as n approaches infinity of the sum where k equals 0 to n minus 1 of f of x sub k times delta x. The function f is called the integrand. The numbers a and b are the limits of integration, and the variable x is the variable of integration. If f is the rate of change of a quantity capital F, then the integral from a to b of f of x dx is called the total change of capital F from a to b. If f of x is greater or equal to 0 for all x on some interval ab, then the integral from a to b of f of x dx can be thought of as the area under the graph of f over the interval from a to b. For example, the green shaded area in this diagram. As an example, let's compute the area under this curve between 2 and 11. If we use subdivisions of delta x equals 1, we have a bunch of intervals that have height 2.5. For example, the interval from 2 to 3 and the interval from 6 to 7. We have some intervals at height 2. For example, the interval from 4 to 5, 8 to 9, 9 to 10, 10 to 11, each of those has area 2. Our diagonally shaped intervals, for example, the ones that are from 3 to 4 or 7 to 8, those have area 2.25. Area 5 to 6 also has area 2.25. So if we add all these up, we get the area from 2 to 11 under the curve of f prime of t dt is 2 sections of height 2.5, 4 sections of height 2, 2 sections of height 2.25, and 1 section of height 2.25 for a total of 19.75 units.